Good morning, everyone. All right, welcome to class. Let's see, what's the plan for today? Okay, so I'm gonna start by taking any questions you guys might have for quiz 6, and then go over some examples from section 3.8, right? So that was the plan for you guys to kind of pre-watch the lecture for section 3.8, and then we can go sort of, you can ask questions, we can go over some examples for that one. Okay. All right, so if you want to speak, unmute yourself or chat things. All right, I have one already. So can I look at number 14 on quiz 6? Okay, so let me pull that up. I'm going to share my screen. Let's see if I can find. Here's quiz 6. All right. Fit it on my screen here. Number 14. All right, so this has to do with the number of strings of zeros and ones. Okay, let me put it over here so I have more space. There you go. So this problem says the number of strings of n zeros and ones that contain an even number of ones is 2 to the n minus 1. Prove this fact by induction for n is bigger than or equal to 1. All right, so let's see what this problem is actually saying. Okay, so we have strings of zeros and ones, right? And we're looking in particular for those strings that have an even number of bits that are ones, right? So, so our basis case right here, the basis case would be that proposition when n is 1. Okay, so the n represents how many bits are in my string. So for n is 1, then I'm going to have a string with just 1 bit, 1 character. All right. So what are my options here? So how many possible strings of length 1 do we have? Anyone?
2.
2, right? I could either have a bit strength of length 1 that has a 0 in it, or I could have one that has a 1 in it, right? So, but I'm particularly interested in those bit strings with an even number of ones. Okay, so which one of these have an even number of ones in it? So this first one or the second one?
First one.
Yeah, the first one. So it's like the first one has no ones in it, 0 ones. 0 is an even number. Okay, so this one has an even number of ones. All right, so does it fulfill this formula? Okay, so does a bit strength of length 1 with n equals 1 fulfill this formula? So we plug in n is 1 in here. And we get 2 to the 0 is 1. Okay, so we see that we sort of get the basis step is correct. So if I actually look at the string, there's only one with the even number of ones. And the formula tells us that there should be just one string with the even number of ones. All right, so now we're going to go to the inductive step. The inductive step says that we're going to assume pk is true. Okay, so let's see what pk means. Okay, so k gives you how many bits are in my string. Okay, so k means that I have a string of length k. Okay, so I'm going to have 1, 2, 3, 4, 5, so on. I'm going to have k different bits in here. And I'm only looking at the strings that have an even number of ones. And the formula says that there are 2k-1 options of this length that have an even number of ones. Okay, so we're assuming this is true. All right, and now we have to prove that this is true. So prove that the pk+1 statement is true. Okay, so we're expecting that a string length of k+1 bits would have, if I plug in k+1 in here, would have 2 to the k bits. So that's what we're looking for. We're trying to show that this answer comes out, okay? So let's build our strings of length k+1, okay? So we're going to, again, sort of use what we know here for the pk statement, right? So, so let's look at the kind of strings that we have of length k. So we have strings of length k. Okay, how many do I have in total? So not thinking, do they have an even number of ones or odd number of ones? How many are in total? What do you think? So k bits, how many options for each? Well, they can be zeros or ones. So how many total options? Anyone can help me with this one? All right, sorry guys, the internet's dropping me off, so it just comes back a few seconds later. So there'll be a couple of interruptions during class. All right, let's see. Not seeing my chat. Okay, just give me a second. Let me make sure the chat is showing. There we go. And my screen again. Okay. All right, so that question was, for a string of length k, how many options are there in total? How many different ones are there in total? Anyone? Good. So I have 2 options for each, right? 1. Yeah, exactly. 2 to the k, right? So because I have 2 options for each bit, and there's k of them, so 2 times 2 times 2 times 2, k times is going to be 2 to the k. All right. Sorry, I seem to have lost my ability to write. Let's see, let's do this. Okay, so 2 to the k in total. All right, now let's break them down into the strings that have an even number of ones and the strings that have an odd number of ones, okay? So from here, or just from figuring it out, we know that there are 2 to the k-1 strings of length k that have an even number of ones. And how many strings of length k are there who have an odd number of ones? So if there's 2k minus 1 strings that have an even number of ones, how many will have an odd number of ones? Right, the same, right? Basically, it's just we have sort of 2k in total. Half of them are going to have an even number of ones, half of them are going to have an odd number of ones. All right. Okay, so now basically we're going to build a string of length k plus 1. So kind of from my strings of length k, I'm going to add one more bit to that string to make a string of length k plus 1. So I have 1, 2, 3, 4, whatever. This is length k. I'm going to add 1 at the end to make a length of k plus 1. Okay, so let's look at each option. All right, so for the ones that already had an even number of ones, to keep it with an even number of ones, what would I add at the end? All right, a 0, okay? Right, so for those I have to add a 0 at the end, but the important part is that I only have one choice for the bit that goes at the end, okay? So I had 2k minus 1 options here, but this last one doesn't increase the number of options because I'm forced to put a 0 in there. So I still have 2k minus 1 choices that come out of this, right? Even if I increase the string length by 1. All right, let's look at so the strings that had an odd number of ones, right? So I had the k bits here, and there were an odd number of ones in here. What do I need to add for the last bit to make it with an even number of ones? Yeah, you need to add a 1 at the end, okay? Because you only have one choice, again, you had 2k minus 1 choices for this, you multiply by one choice, it's not going to change the number of choices. You still have 2k minus 1 choices, right? But now you need to add these together, okay? So now because I'm looking how many strings of length k plus 1 have an even number of ones, I have the ones that I formed with the original ones that had even number of ones by adding a 0 at the end, and that was 2k minus 1. But then I had an additional 2k minus 1 that I made out of the original ones that had an odd number of ones by adding another 1 to them. So now when I add these together, I get 2k minus 1s, which makes 2 to the k. Right? So we can see that we reasoned our way to showing that the formula holds true for pk plus 1 also. Okay, so this is what we're trying to get to. All right, so notice that this is an induction proof, base is an inductive step, but this one is not so much algebra, not so much substituting and plugging sort of one thing into another or adding, you know, something to both sides of an equality. It's more reasoning and logical, but it still follows the inductive process. All right, any questions with that one? Okay, we're okay? All right, any other questions from quiz 6 problems? Let's look at number 16. So number 16 is sort of a problem that we've seen before a couple of times. Right, so there are n people in the room. N is bigger than or equal to 1, so at least one person, right? And they all shake hands to one another. Prove that n times n minus 1 over 2 handshakes will have occurred. All right, so This is the handshake problems that we basically saw on the first day of class, right? So we want to look at how the handshakes are occurring, right? So if you have the basis case, it's P1. Okay, so if we have one person, right, then it makes sense that there are 0 handshakes because the person is not going to shake hands with themselves. And if we put in the formula, 0 times -1/2 gives me 0. Okay, so that kind of fits into the formula. It makes sense. All right, now for the inductive step. Right. So we're not sort of really like, we're given the end results, but we're not sort of told that this sum equals this or anything like that. So we kind of have to think about how the handshake problem works. All right, so let's look at a few different values of n to see what happens. So basically we saw that with n is 1, that's one person, there are 0 handshakes, right? If n is 2, so another person comes in the room, there were 1 handshake. And if n is 3, then we have, how many handshakes is that? Is this third person is going to shake. It was the first handshake between 2 people, and then this third person that comes in is going to shake the hands of the 2 people already in the room. So that's going to be 3. Now if there's 4 people, and as the 4th person comes in the room, 3 handshakes already occurred. And the 4th person is going to shake the hand of all right, the 4th person is going to shake the hand of the 3 people that are already in the room, so that makes it a 6. Okay, so basically we see that we're adding to whatever happened previously. Okay, so let's look at n is 5. So for 5 people, 6 handshakes already happened, and the 5th person shakes the hands of the 4 people who are already in the room, so that's 10. Okay, so you can see that sort of it's adding up, right? So we're getting 1 plus 2 plus 3 plus 4, blah blah blah. So basically you're adding for each person coming in, you're adding n minus 1. Okay, so kind of how many people were in the room previously. Okay, again, it was sort of, we've looked at this problem before a couple of times. All right, so basically what we're trying to prove here is that if I add 1 plus 2 plus 3 plus 4 plus all the way to n minus 1, this is going to give me n minus 1 over 2. All right. Okay, so we see that it worked for when n was 1. All right, so it's like n is 1, 1 person in the room, then we get a 0. Okay. Actually, this should have been 1 and 0. I plugged in the wrong thing. N was 1, not 0. All right, so now the inductive step says that we're going to assume pk is true. So pk goes from 1 to 2 plus 3 all the way to k minus 1. And this is k minus 1 over 2. Okay, so this formula is assumed to be correct. Okay, let me change color. And now pk plus 1, we're going to go to one more person. Okay, so this on the left-hand side, I go 1, 2, 3, k minus 1, and then one more person is going to go to k. And this side, we're going to plug k plus 1 in here. So we have k plus 1, k plus 1 minus 1, which is k over 2. Right, so we need to show, we don't know that this equality holds. We need to show that these are equal to each other. Okay, so we do that substitution thing. We're going to substitute this part here, right, is this part here, and we know that's equal to this. So this replaces that sum. So we have k and k minus 1 over 2 plus k, which comes from here. And we need to show that this simplifies to that. Okay, so we find the common denominator. Okay, we're going to say k squared minus k plus 2k over 2. Combine into one fraction, simplify it. K squared plus k over 2. Factor out a k. And we get k plus 1 in parentheses. And we compare them and we say, yep, it's the same thing. And that basically that proves that this is true using the fact that pk is true. So the inductive process is finished. Okay? All right, so probably kind of just coming up with this bit or remembering the handshake problem means this from what we were looking at before. And then after that, it just kind of becomes a standard inductive proof. All right. Any questions with that? Okay. All right. Any other questions from quiz 6? You guys are very quiet this morning. All right, let's see. 6D. I'm not sure I understand. So how pk plus 1 left side? For Reed, I'm not sure I understand your question. But I can come back to it. Let's look at 6D. All right. Sorry, cool. So 6D. So we're given these propositions, and we want to figure out the truth set of if Q, then R. Okay. So we're looking for this truth set right here. All right, so there is a formula in this section. So section 3.6, I think so, on the truth sets, that showed you how these are related to the sets, okay? I don't have it in front of me, but you can look it up. But if you kind of think of using, changing the conditional to a or, this means not Q or R, okay? And the or with the truth set changes into the union of the not Q set and the R set. So basically, we're looking at the union of the truth set for not Q and the truth set for R, okay? And the truth set for not Q is the complement of the truth set for Q and then united with the truth set for R, okay? So this is like a relationship that sort of I gave you in a box somewhere in section 3.6, okay? All right, kind of same as like this one was the truth set for P and Q is the truth set for P intersect truth set for Q, right? So let's look, what are the truth sets here? So we need the Q and the R truth sets. So if Q, it's n is bigger than 17 over 2. And we're looking at natural numbers, right? So the true set for Q is 8.5, 9, 10, 11, 12, and so on. 9, 10, 11, 12, dot, dot, dot. So that's the true set for Q, right? So that means the complement of the true set for Q is all the natural numbers that are not 9 and above. That's going to go 0, 1, 2, all the way to 8. Okay, so that's the complement of the Q true set. All right. Now the true set for R. So R is n is a divisor of 18. So anything that divides 18, that's a natural number. So 1, 2, 3, 6, 9, and 18. Okay. Does 0 count? Anybody put 0 in there? Nope. Okay. Let's start at 1. Okay. So now we're looking at the union between this one and this one. Okay. So the union between those two is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so basically everything in here, but then the true set of R also has the 9 and the 18 that were not in the original one. So everything in complement of Q with the addition of the 9 and 18 from the R. Okay, and that's it for that one. That's 60. All right. Any questions with this one? Okay. All right. All right. Any questions about, before I kind of start looking at 3.8, any questions about what's coming up this week? Questions about the test? Oh, okay. So, sorry, there was. I erased everything. So Yuval, you said you thought it had to be less than 9. Did I put 3? Did I put the 9? I included 18. Okay, so let's see, let's do this. So TQ was 9, 10, so on. The complement was going up to 8. Oh yeah, 18 was part of R. The true set of R is 1, 2, 3, 6, 9, and 18. So if when I do the union of these, the 9 comes from here, not from here. Okay, so when I do the union, I'm including everything in here and in here. So it's going to include go up to 8 and then also the 9 and the 18. Okay, cool. All right. Okay. So yeah, let me just look at. Yeah, you can use that builder notation for your answer if it's helpful. But sort of listing it is fine too. Okay. All right. So let me let's look at the canvas shell. Okay. Right. So we are looking at. Let's see what did I say we're covering this week? Okay, so today's Wednesday, right? So we're going to Your quiz 6 is due in Canvas by midnight, and Pi the extra credit if you're working on that. Okay, and then tomorrow your second test will become available in Canvas by noon, and it will be due by noon on Friday. So you have 24 hours to complete it. Okay, so let me show you where to find it in Canvas. So it's gonna be here. Okay, so kind of just under the front information, then test 2 will be right here. Okay, so you're gonna click and there's gonna be a file on there that you're going to find the test questions, and then you're gonna write it, take pictures, and then upload it. Okay, so Suki, there's no logging in and logging out. I'm not sure if you guys are sort of clearly understanding what the test is gonna be. It's not an online exam. It's in here, you're going to open a PDF file that's gonna have like 11 questions on it. And you're gonna do the questions on pen and paper. You're gonna take a picture, or you're gonna type your answers in a document, and then you're going to submit it. Okay, so you're going to, it's basically the kind of test that you took for test 1 in class, only you're doing it at home. You can use your notes, but no other help, like don't talk to other people during the test, and don't use the internet, and you're gonna upload it and it comes to me, okay? So it's not a countdown, not gonna close on you, it's just the file is on the computer instead of me handing it to you, okay? All right, so Chris, why am I not doing it online? Because I don't have an online test bank for discrete math. It's like for algebra, there are loads there, but for discrete math, not so much material. And I didn't have time to build one in Canvas. I don't think you can show step-by-step truth tables or proofs with justification on an online test. So we're doing it on paper. Wayne, yes, Word doc or PDF are both good. Anything or images, like if you take a picture of your piece of paper that you did work on, then as long as it's clear and I can see all your work, then that's fine. Okay. All right. So I put up quiz 7. So after today, you should probably start looking and working on quiz 7. That's going to be due after the break, but you know, the more you can sort of do in time, the better. Let's see, we're not worrying about projects for now. So we're going to start looking at material that's not on the test. So the test is sections 2.5 up to 3.7. Anything that we're sort of covering today is going to be on the next test, okay? All right, so we have a couple more sections in chapter 3. So 3.8 is on quantifier and 3.9 is on proof methods. So let's see. Okay, so we're gonna look at section 3.8 today. All right, let me pull it up. Oops, not that. All right, so 3.8, we're looking at quantifiers, and I have the pre-recorded lecture that you guys have either watched or can watch later. So my intent is not to go through every of these examples because they're already explained somewhere. But I want to kind of give a gist of what the concepts are and give you guys some examples to work on. Okay. We're looking at the existential and the universal quantifiers. Okay, so this is kind of a way for us to look at the predicates, the sort of the prepositions that have variables in it over the universes. And the existential quantifier is basically a generalized disjunction. Okay, so this is like there exists n in a universe for which p of n is true. Okay, so this is like a disjunction. Right, so as long as you have a universe, a proposition of a universe where the truth set of the proposition is not empty, it's not the null set, then you can see there exists an n in the universe where p is true for that n. Okay, so basically you're saying that I could have p of n1 or p of n2 or p of n3 and so on. That is true. So that's basically saying the same thing. Okay, so the existential is like a generalized disjunction. So you're doing disjunctions of the proposition for all the values of n in the universe. Okay, and sometimes you'll see the universe specified and sometimes you don't. It's kind of implied or mentioned somewhere else. All right, now for the universal quantifier, that's this upside down A. All right, so this is Pn is a proposition over the universe where the truth set of P is the whole universe. So basically we're talking about tautologies. Then you say that for all n, Pn is true, okay? So basically this is a generalized conjunction. It's basically we're saying that P is true for N1 and also true for N2. It's also true for N3. It's going to be true for all values of N in the universe, okay? So kind of these symbols are kind of a shortcut way of saying the disjunction and conjunction of the prepositions for all N in the universe that we're interested in, okay? So we're gonna see the format. We're gonna see how this works with statements and with some proofs, with negations and so on. Okay, so when these are true and false, okay, so the universal statement is true if the proposition we're interested in is true for every n in the universe, and it's false if you can find a counterexample. It's false if you can find just one value of n for which the proposition is false. Okay. All right, and for the existential quantifier, the existential of a proposition is true if you can just find at least one n in the universe for which the proposition is true. And the existential quantifier is false if it's false for every single n in the universe. Right. Okay, so let's look at this here. All right, so this says, what is the truth value of this? Okay, so this, if you read it, this says that there exists a value of x in my universe for which x squared is bigger than or equal to x. Okay, so let's look at, it says the domain consists of all real numbers. Okay, so first we're gonna look at the universe being all real numbers. Okay, so we're gonna try to figure out if this is true. Okay, so for all real numbers, can I find a value of x for which x squared is bigger than or equal to x? All right, and then we're gonna look at the universe of integers. Same question, can I find an integer x for which x squared is bigger than x? All right, what do you think, guys? Is this true for the real numbers? Odds are good. Yes. Right. So odds are good because I could say, well, how about if x is 2? And I know 2 squared is going to be bigger than 2. Okay. So yeah, I could find the value of x for which that is true. And same for the integers, right? Same thing. I could also take 2. I can find a bunch of integers for which that is true. All right. Now for B, let's look at the universal quantifier. See how this is different. Right, so let's look at our universe being real numbers. So this one says that this inequality has to be true for every single real number. Okay, so now, is that true? So the other way you can put that question is like, can I find a value of x as a real number where this is going to be false? Right, so 1/2. So this is going to be false because 1/2 is a counterexample. So if I take x to be 1/2, then if I square it, this is not going to be bigger than 1/2. Okay, actually any value between 0 and 1 is going to break that. Okay, everything else is fine. Like if I pick 1 and above, then the square. If I pick negative numbers, then that's going to hold, but any real numbers between 0 and 1 is going to break it. Okay. How about if my universe is the integers? Is this going to be true or false? This is going to be true, right? Because we saw previously that only numbers from 0 to 1 will break the inequality, but there's no integers between 0 and 1. So it holds for 0, it holds for 1, it holds for any other integers. So that's going to be true. So you can see the universe is really important when we talk about these predicates, these propositions. All right, cool. So that's the idea. With essential universal quantifiers, and we can sort of find the truth values of them kind of based on their definition. So again, always kind of think of the universal as a conjunction and the existential one as a disjunction. All right. Okay, so let's go do some here. Yeah, let's look at negations, okay? So when we negate quantified propositions, this is because they're basically disjunctions and conjunctions, we're applying De Morgan's law. Okay, so this here says that if I negate a universal quantifier, then so in order to distribute the negation to the proposition, it's going to turn into an existential one. Okay, so remember the universal quantifier was saying that the propositions is true for n1 and for n2 and for n3 and for all the n in the universes, right? So basically this is expanding it out. That's what it says. And then De Morgan's law says that to distribute the negative, the ands are gonna change into ors. So this is why this is going to an existential, because when it distributes, say it's not going to be true for n1, or is not going to be true for n2, or is not going to be true for n3. Sorry, the indexes should be on the n. So universal, change it to existential of the negation of the proposition. And if you negate the existential, same idea with De Morgan's law, it's going to turn into universal statement for the denegation of the propositions. Okay, so let's look at example 7 here. So let's translate. There's an honest politician and then negate it. Okay, so to translate something like this, we're can define our universe. Okay, so let's say X is all politicians, or X is politicians, and H of X is honest politicians. So there is an honest politician would be translated as there exists a politician such as that being honest is true. Okay, so that's the translation of this. All right, now let's negate it. So if I negate, all right, just a second. So Michael, what does the subscript U mean? So this is the universe. So sometimes you'll see this universal quantifier given, it's like there for all x in integers, then you get the statement P of x is true. Okay, so sometimes you have a subscript there that kind of denotes the integers. Most of the universe, most of the time not. Most of the time the universe is implied or it's in context or you're saying it on the side. Okay, so you can put like part of the statement or beside the statement. Okay. All right, so we're gonna negate this statement right here. Okay, so when I negate the existential, the negation kind of distributes in and it becomes the universal statement of the negation of the proposition. Okay, so now we can kind of think, what does this say? So what does this statement say right here? Anyone care to try it out? All politicians are what? Are not honest. Okay. Okay. So you can say there is no honest politician, or all better kind of, if you kind of do direct translation here, every politician or all politicians are dishonest. Okay. So you can see how negation works in sort of changing an existential to a universal of the negation. Okay. Any questions with that one? All right. Okay. Yeah, not a good time to talk about politicians. All right, so let's look at these mathematical statements and do the negations. Okay, so if I have this, okay, so this says for all x, x squared is bigger than x. Okay, and we said that this is true if we're talking about the universe being integer, but it's false if we're talking about the universe being real numbers. But let's negate the statement. So kind of not really worrying about its truth value. Let's negate it. So if I negate it, then this is going to turn into, let's not say imply, it's going to turn into this. So the existential, and then the negation goes to my proposition. So you can see how it's set up. So we have the quantifier, and this is like a typical element in my universe. And this right here is P of x. This is the proposition that we're interested in, okay? So the negation goes in front of the proposition. So this is saying there exists an x for which this is not true. So there exists an x for which x squared is actually less than or equal to x if I actually negate that inequality. Okay. All right, so let's look at this statement here. So this says there exists x for which x squared equals 2. Okay, so this would be true if x is real. It would not be true if x was an integer, right? But let's negate this. So let's do the negation of that statement. So if I put a negative in front, this will turn into universal x negation of my proposition. So this says for every x squared is not equal to 2. So for every x in my universe, we can have x squared is equal to 2. Okay? So those are some examples of negating the universal and the existential quantifiers. So this sort of summarizes this, the Morgan's law for quantifiers. It says what I was talking about. All right, questions so far? All right, let me clear this. So a lot of the stuff that you're gonna do in this section, with sort of the problems, are translating and negating and looking at the order of things if there's more than one quantifier. But let's do some translation. Okay, so we're going to look at every student in this class has studied calculus. And again, the universe is important in how you translate. So let's look at the universe be all the students in this class. Okay, so let's say X is a student in this class. Okay, so that you can see that specifies the universe right there. And let's say C is the proposition that somebody has studied calculus. So to translate every student in this class has studied calculus, every is the universal quantifier. X means student in this class because that's kind of the universe that we're interested in. And then the proposition. So every student in this class, this statement is true, has studied calculus. All right. Let's see what happens when we change the universe for the universe to be all people. Okay. So now X is a person. Okay. So it could be any person in the world or other planets. Okay. But now we basically need two preposition. We need one preposition that says that X is a student in this class. And the same one as before, that X has studied calculus. Right. So now when we translate every student in this class has studied calculus, we said for every person in the world, and now we have to kind of specify that the person is in this class, okay? So for every student in this world, if the person is in this class, then they have studied calculus. So kind of this becomes a conditional. So you can't you wouldn't put and, okay, because that would mean for every person in this world, they are in this class and they had studied calculus. So that would be a lot of people in our class. But it's a conditional. So for every person, if they're in this class, then they have studied calculus. Okay, so how the translation goes for if the universe changes to all people. All right. Any questions with this? Yes. So yeah, when you translate, this is really helpful to this kind of defines the universe. So when you say X is a student in this class or X is a person, it specify what the universe is, right? And then you can translate any propositions. Can I explain when is the negation true part? Okay, yes, so let me go up. Yeah, so this summarizes the negations. Okay, so if I'm negating the universal quantifier. So if I'm saying it's not true that for all n in the universe, P of n is true, okay, that basically means when the negation is true, it means that for every n, P of n is false. There is an n for which, okay, I gotta look at these because they seem to be inverted, because the negation would be true if there is just one value for which P of n is false. And for this one, the negation is true if, I think these are inverted. Okay, so I let me check on that. But I think they should be backwards. Because yeah, if I'm negating for like all values of n, P of n is true, it should be that the negation is that there is one particular n value for which is false, and that negates it. Okay, so yeah, I think you're right there for pointing that out. So let me just, I'll check on it and I'll revise the lecture notes if necessary. But I think those should be inverted. Okay, cool. All right, so let me go over one more translation. Okay, so let's look at some student in this class has visited Mexico. So let's look at this this one first, and take the universe to be the students in this class. Okay, so we're going to say X is a student in this class. And we need the statement M of X is that X has visited Mexico. Right? So some student in this class has visited Mexico. You say there exists a student in this class that has visited Mexico. Okay, so that's the translation there. Okay, well, if I change the universe to be all people, so if I say X is just people, then I need, again, D is that X is in this class. So that's a statement there, and I need M is that X has visited Mexico. Then the translation would be there exists a person who is in this class and has visited Mexico. Okay, so that would be the translation there. Okay, so notice that this is different than what we were looking at. So above here, when I looked at every student in this class has studied calculus. So with every, when you take the universe to be all people, we had every X, if they're in this class, then they had studied calculus. That uses a quantifier. But if it's a existential, there exists a student, a person that they're in this class and they've gone to Mexico. So with an existential, that translates to a conjunction, to an and. Okay, so it's a kind of a different operation, whether you have every with the universal or some with the existential. Okay. All right. So let me see if I can find something for you guys to try. Well, let me go over the next part first. No, okay. Well, let me put up. Okay, let me clear this up. All right. Okay, annotate. All right, let's say that X represents people, and I have f of X means that X is friendly, and T means that X is tall, and A means that X is angry. Now, so I want you guys to try translating. First one, some people are not angry. And second one, all tall people are friendly. And the next one, if a person is friendly, then that person is not angry. All right, so go ahead and take a couple of minutes to come up with translations for these. All right, so let's look at the first one. So some people are not angry. Any ideas? Okay, so some, right. Some means the inverted E thing. X is people and not angry. So some people are not angry. Cool. All right. Anyone for all tall people are friendly? All. X, that's good. Okay, so tall people. Yep, I would go with that. So yeah, for all people, if they're tall, then they're friendly. Perfect. Okay. All right, how about 3? So if a person is friendly, then that person is not angry. Right, yeah, so it's right. So friendly, then not angry. Okay, but how about the front stuff? Is that a universal or an existential? So am I saying there is one person who's friendly and not angry, or does this mean for all people who are friendly, then they're not angry? Yeah, it's a universal. Cool. All right, so good. So that was a little bit of translation. Um, so these are fun, but they can be confusing. So they're neat to look at. All right, so let's look at what happens. Okay, multiple quantifiers. Okay, so if a proposition has more than one variable, so if we're looking at x's and y's and z's and so on, then you have multiple quantifiers. Okay, so you can have multiple universal quantifiers, you can have multiple existential, you can have a mix of both. Okay, so the order sometimes matters, sometimes it doesn't. So if you have quantifiers of the same type, then the order doesn't matter. So for all x and all y, you can say for all y and all x, p of xy is true. Okay, so that means that pxy is true for every pair xy. Now, but if you get mixed quantifiers, if you have the universal and the existential, then if you switch them around, the order changes. Okay, so you got to be careful with the order there. And again, if you have 2 existentials in a row, then the order doesn't matter. So let me look at, okay, let me look at another example. Let's say, okay, let's look at this statement. Let's say pxy is the proposition that says x and y are real numbers such that x plus 2y equals 5. Okay, so we want to determine the truth values of each of these. So let's write this down. And then we're going to look at this one. Right. So we want to determine the truth values of each. Okay, so let's see what the first one says. The first one says that for all x, for every x, there exists an y, so that this statement is true. So for every x, there exists one y. It doesn't have to be exactly one y. You could have more than one solution. But for every x, there exists a y such that the equation x plus 2y equals 5. Okay? So this is a true statement because for every value of x that I pick, I can find a value of y that makes that true. In fact, basically you solve for y. So if I solve for y here, 2y equals negative x plus 5. we get y equals -1/2 x plus 5/2, okay, which is a straight line. So for every x, a real number, then I can find the y value that makes that equation true. Okay, so this is a true statement, right? Now let's look at if I turn it around, okay? So this says there exists an x such that for all real number y's, that proposition is true. So this says that there is an x value. So this is a particular x value. Let's call it x naught. Okay, so this is not a variable anymore. It's just a particular value of x such that this statement x plus 2y equals 5 is true for all real y values. Okay, we can see that this is false because there is no value of x that will make this statement true for every single value of y. So that basically means that if I solve, that means that this statement, like I can find a particular value of x, like 1, so this statement will be true for every single value of y. And it'll be true for one particular value of y, but it will not be true for every real value of y. Okay, so it's kind of like saying that this equation right here has an infinite number of solutions, which it doesn't. It just has one solution. All right, so kind of the switching around of the universal and existential gives a different meaning to your statement. Okay, so you have to be careful with switching it around. All right, any questions with that one? Let's go back here. Okay, so I want to make sure to cover the stuff at the end. Okay, so there's more. Again, these are examples are on the pre-recorded lecture. I'll show you where to find it before the end of class. But I want to look at the rules of inference. So those are the laws of logic. So just with the regular propositions without variables, we looked at the laws of logic and sort of how to prove things with propositions. But that can be extended to predicates, to propositions that have variables in them. And those are a lot more useful because that's what we usually do in math. We have things with variables that we try to prove that they're right or wrong. So we still have like things like the law of detachment and direct reasoning that we can use, but we're sort of kind of adding 4 more in here. And these allow us to kind of switch between a proposition over a universe, something with variables, to ones that are like regular propositions that are true for one particular instance. Okay, so this first one, this is the universal instantiation. So it says that if I have this statement that for all x, p of x is true, then this implies that p is going to be true for a particular value of c. Okay, so if it's true that all students in this class are brilliant, then it's also true that Suki is brilliant, or Jonathan, right? So it's kind of basically you can go from everybody in the universe to a particular student or a particular instance in the universe, right? The second one, universal generalization, says that if this proposition, this statement is true for an arbitrary value of C in the universe, so not for a fixed one, but for anything that you pick in the universe, then you can say that for all x, P of x is true in the universe. So this is generalizing from a particular value to, from an arbitrary value to all values. Kind of same works for existential. So going from all to one. So if you say there exists an x and p of x, so p of x is true, then P is going to be true for some element in E. So that's existential instantiation. And going backwards, if P is true for one particular element in C, you can say that there exists an X such that P of X is true. So again, sort of these allow you to switch between things with variables and things with not variables. So kind of from the general to the instant, from the instant to the general, or from the particular to the general. And we can sort of look at the law of detachment and indirect reasoning. But let's look at a couple of examples first. Okay, so let's see how these are applied. So 14 says, I have the premise everyone in this discrete math class has taken a course in computer science. Okay, so if I translate this, so everybody in this discrete math class. So if X is a person, if they're in the discrete math class, then they have taken a course in computer science. So that's the translation. And then it says Maria is a student in this class. Okay, so you say that by saying, oops, that's not right. Okay, D Maria. All right, so this is saying that Maria is a student in this class. So DX stands for X is a student in this class. So if I want to pick a particular student, that would be D Maria. Okay, D is a student in this class, or Maria is a student in our discrete math class. And we want to see if this implies the conclusion that Maria has taken a course in computer science. Okay, so C Maria. Like that. Okay, so we can see that this, you can kind of think of it in steps. Okay, so basically, I need white paper. Okay, let's see. Oh, good. It saved it there. Okay. So if I have this will imply sorry. If I have this statement here, so the general universal statement, so if a person is student in this class that had taken computer science, you can change this to, this will imply that if Maria is in this class, then she has taken computer science. Okay, so this is an example of this first rule right here, the universal instantiation. So if it's a statement is true for all people in the universe, it's going to be true for one person in that universe. Okay, so this is the universal instantiation. Universal instantiation. Okay. All right. So what this does, let me just call it for M, is that it changes our kind of general, the predicate statement into one that's a regular proposition. So because this is for one person, this is basically a P then Q statement that we're familiar with before. Okay. So now we also know that this is true. So we basically know that the P statement is true, and this is going to imply this statement with detachment. Okay, So you can sort of apply very similar rules of logic that we're applying before with like regular proposition by using these universal and existential instantiations from basically the purpose is to change a general statement for X into a particular statement for one particular element and person and use the regular rules of logic. And then we can also translate them back to general statements. Okay. So this is kind of really summarized in here, like with these rules right here. So instead of kind of going step by step, you can sort of do it all at once. So if you have this universal statement that for all x, if p of x, then q of x, and you know that it's true for one particular person, then it's going to imply p is true for one particular person, then it's going to imply q is true for one particular person. So you can kind of skip a step. So that's the law of detachment. And then the law of indirect reasoning also applies that way. So universally, I know if P, then Q is true for all people in the universe, and it's not, Q is not true for a particular person, then P is not going to be true for that particular person. So that's an indirect reasoning argument. All right, so I'm going to stop here. Okay, so then for now, so for tonight, finish quiz 6 and submit it, and then tomorrow check for your test 2. All right, so I think, yeah, I'm making it available to you guys at noon. Okay, and you should work on it, submit it by noon on Friday, then go on spring break, relax. When we come back, or you can start looking at quiz 7. Okay, quiz 7 is section 3, 8, 3, 9, and 4, 1. So when we come back, we're going to look at those sections. All right. So I'll stick around for questions. So I have office hours next, but I'll stay around for questions. Stop sharing. There we go. You have a nice spring break too. Yeah, let me know if you have if you're having problems finding the test or downloading it or uploading it. I'll be online tomorrow, and I'll be checking my email Friday and over the break. Okay. See you later, guys. Oh, yes. So to answer your question, the indirect proof can be just adding one more line at the end with the negation of the conclusion and show contradiction. So that's kind of, that will always work and that's valid. But so the purpose of indirect proof is to kind of make like fewer steps for giving a proof to a theorem. Or sometimes direct proof is really awkward and not practical, and indirect proof is a lot better. So if possible, try to find ways to do the indirect proof that's not just like a replica of the direct proof. All right, let me look it up. Okay, so 6. Or E. Yes. So what 4E is asking you, it's asking you to list all the subsets in the power set where the cardinality of the subset A is the same as the cardinality of the complement. Okay, so let's list. So if you look at the power set, it's going to be the null and then all the sets with one element in them. Okay, and then you have the 2 element subsets, 3, 1, 4, 2, 3, 2, 4, 3, 4. Okay, and then 1, 2, 3. Oops. 1, 2, 4. 1, 3, 4. 2, 3, 4. And then 1, 2, 3, 4. Okay, so that's the power set. Okay, so what this says here, so A is an element of the power set. A is any subset in the power set. So it's saying for which of these subsets in the power set, the size, the cardinality of A would equal to the cardinality of its complement. Okay, so for example, if I say my set A is 1, then the cardinality of 1 would be 1 because there's one element in it. If I look at the complement of set 1, this is going to be 2, 3, 4. So all the elements in the universe. So the universe is 1, 2, 3, 4, right? That are, so yeah, 2, 3, 4 is the complement of A. And the cardinality of AC is going to be 3. Okay, so obviously it's not going to work for any of the 1 element sets because the cardinalities of these sets are 1, but the cardinalities of the complements are going to be 3. Right? If I look at the 2 element subsets, the cardinality of those subsets is 2, and the cardinality of the complements is also going to be 2, because if I look at 1, 2, the complement of it is going to be 3, 4. If I look at 1, 3, the complement is going to be 2, 4. So these are the ones that are going to match. For the ones that have 3 elements, so the cardinality of something with 3 elements is 3, but the cardinality of the complement is going to be 1. So those don't match. And then the ones at the end are sort of, the cardinality is 0, the cardinality of the complement is going to be 4, and the cardinality of this is 4, the cardinality of the complement is going to be 0. So the only ones that they're the same size set for the set itself and its complement are going to be the one with 2 elements in them. So just those 6. All right, does that make sense? All right. 1C. Okay, let's look at 1C. So indirect proof. So we have our propositions, S or P, Q, and I'm going to negate the conclusion, and we want that to be a contradiction. Okay, so let's see. So when I do by indirect, I start with the conclusion negation and sort of try to work backwards. So let's see what this is. So if I negate this, first I'm going to change this into a disjunction. Okay, so that's the conditional equivalence. Okay, because now I know how to negate it. Okay, so if I negate that, it's going to be the Morgan's law. So it's going to be S and not R. Okay, so because this is a conjunction, this is going to imply S, and it's also going to imply not R. Okay, so that's the conjunctive simplification. All right, good. So these might be useful because you have these single things, you can use them, right? So for example, if I have not S or P and I pair it up with the S, then this is going to imply P, right? Because that's the disjunctive simplification. All right? And then I'm going to take that P and pair it up with the first one. If P, then Q, then R. And P, this is going to imply the second bit. And this is detachment. All right. Now I'm going to take this one and pair up with the Q. So pair these up together. So I have if Q, then R, and Q, this is going to imply R. This is detachment again. And then I see my contradiction. So I have not R here, and I have R there. R and not R is my contradiction. All right, so that's an example of indirect proof for that one. I think I found the direct proof for part C a lot more awkward because like I had to break this up, this double implication. We kind of have to change it to ors and then switch them around and change them back to implication. So it was a bit awkward to do. So to me, negation is a lot easier for this one, or the indirect proof. Oh yes, yeah, the conjunctive simplification, if you look at that law table, it implies both, right? If it's a proposition and another proposition, is going to imply both of them, okay? So I always do kind of do both conclusions because I'm probably along the way I'm gonna need to use both of them um, as part of other steps. So yeah, it's good to have it imply both of them. So it's the conjunctive simplification allows you to separate them. The disjunctive simplification, it's a lot more restrictive. Disjunctive simplification, you need to know that the other one is not true in order to imply that the first one is true. Okay, so let me share again. Sorry, I got dropped off of everything disappeared. Okay, so right, if you have, again, just for general statements, if you have P and Q, then this is going to imply P, and this is going to imply Q. So this is conjunctive simplification. So if you have an and, then you separate them, okay? Which is great, okay? This is like really powerful. Right? But if you have a disjunction, you can't separate them. So P or Q doesn't imply that P is true because Q could be true, right? Or they could both be true. So it's not a clear separation. So for conjunctive simplification, you also need to know something about if you have P or Q and you know that not Q is true, then this is going to imply P. All right, and that's it, right? The other option is if you have P or Q and you know not P is true, then that's going to imply Q. All right, so this is disjunctive. simplification. Okay, but you need to know the second bit. If you don't know that not Q is true, then you can't separate it. For conjunction, you separate them straight away because they both need to be true. But for disjunction, you can only tell that P is true if you know that Q is not true. You're welcome.